Yeah, thanks for the introduction, and thank you for the having opportunity organizing this wonderful KAIST-NTU joint workshop, and hopefully we're gonna have the face-to-face meeting maybe next year in this nice scenery and chilling out. But to have that, one of the biggest challenges that in human society faces actually global climate change and also the rising sea level. So and we have to prevent that in order to get to chill out in this nice beach. So in order to mitigate the global climate change is reduce the CO2, the anthropologic CO2 concentration in the air, and one of the way to directly and nitrogen dealing with nitrogen cycle, as Professor Yan just talked about, is one way to do it. But one of the most direct way to do is actually CO2 utilization to make the useful product. So today I'm going to talk about how to convert utilize CO2 into the value-added product. And to do that, initially I'm going to talk about the techno-economic evaluation of electrochemical CO2 reduction reaction to point out which product should be targeted. And then after that, I'm going to talk about how to produce a multi-carbon product by this project, the process. Okay. Okay. Somehow. Okay. So the electrochemical CO2 reduction is a very simple reaction process. This is very similar to the water splitting reaction. Only difference is that you add carbon dioxide in water. So with the reaction with the CO2 and water, and also the electron from electrocatalyst, CO2 can be reduced to various products depending on the catalyst surface. So for example, with depending on the catalyst, if you have two electrons and two protons are transferred to carbon dioxide, then you can form a carbon monoxide and the formic acid. If the 12 protons and electrons transfer to carbon dioxide, then you can form C2 product such as the ethylene and ethanol. And all these products are well known, the fuels and the plastic feedstock, and sometimes you can use the indium specialty chemicals. So the so to target, since that CO2 reduction can produce many products, you need to target the material, and to do that, you have to consider its environmental impact, and also its economics. In this figure, shows that the life cycle analysis of electrochemical CO2 reduction. For example, in this figure A shows that the global market size of ethylene, ethanol, carbon monoxide, and formic acid versus the carbon emission from the conventional processes to produce these molecules. As you can see here, that as you can imagine, the ethylene, the feedstock material for plastic, like plastic bottle, has most large market size. Therefore, there's a high chance of and also it produces many carbon dioxide emission into air. Ethanol is the second. The carbon monoxide and the formic acid here, I don't know, it's breaking a little bit, but it's relatively occupy relatively small market sizes, and therefore has the small environmental impact. But you can also perform the sensitivity analysis as a function of the energy efficiency of your electrochemical system, and also the the gradient intensity. So gradient intensity means that how much CO2 is emitted in the conventional power plants. And you can see here that, of course, that if you have the so the net CO2 emission from electrochemical process. So if you replace the conventional process with electrochemical process, then you can, depending on energy efficiency of system and the gradient intensity, for C1 product, like the very hard to, yeah, the carbon, the fumate and carbon monoxide, the negative net emission is possible. But unfortunately, again, the C1 product has a small impact in environment. But the ethylene and ethanol, the C2 product, you see that there is a very you need to have very high energy efficiency and also low gradient intensity to make this process environmentally friendly. And secondly, we can also calculate the economics of this process, and it turns out that if you do the sensitivity analysis again, you must have a very highly efficient system to make this process profitable. First of all, you need to have very high current density, as you can see, like at least 300 million per centimeter to drive CO2 reduction. And then you need to have very high the Faraday efficiency. So you need to make this ethylene and ethanol profitable more than 70%. That comes from the separation, the cost, the after CO2 reduction. So in a nutshell, basically all the LCA and the techno-economic evaluation indicate that you need to have high performing and efficient and also selective electrochemical system for CO2 reduction. In order to do that, essentially you need to have the electrocatalyst, the efficient and selective electrocatalyst. And if you look at the periodic table, only a few element is known to reduce CO2 into useful product. For example, copper, gold, and silver. I'm not sure. Okay, the laser pointer is very hard to move, but okay. So the gold and silver and zinc, they are known to produce dominantly produce a carbon monoxide. The indium, tin, and bismuth, as well as palladium, is known for dominantly produce a fumate, and the copper is the only material that produces a hydrocarbon, including methane, ethylene, and ethanol. So this shows that the electrochemical reaction on copper is very complicated. So this shows the electrochemical data on copper foil. So as you can see here, at the low over potential, since this reaction occurs in water, hydrogen evolution is dominant, but with increasing over potential, initially the fumate and the CO, the C1 product evolve, and then the ethylene peaks out at about 25%, and after that, at even higher over potential, methane begin to dominate. So the question, if you want to produce the ethylene and ethanol, then how are you going to selectively produce this control these various the product. So there are many ways to do it, but you can categorize into two approaches. The one is that you can tailor the intrinsic properties of catalyst. For example, you can control the active site. For example, copper 111 is known to produce methane dominantly, whereas copper 100 or other high index planes like 710 or something like that produce the ethylene and ethanol. And it's also known that the grain boundaries, the low coordination sites such as the grain boundaries, and are known for active site for ethylene. And there is some type of impurity, for example, subsurface oxygen beneath the copper is also known, suggested to promote C2 product, but that's under debate. And the second way to control the activity is making alloy, the well-known approach. By alloying, for example, gold and other element in copper, you can actually tune the product selectivity from C1 to C2, and also in alloy, you can use the phase separated alloy system, which also has some geometric ensemble effect to make the C2 product more easier. The second category would be controlling local electrolysis environment. So this, for example, the cations in the electrolyte is also known for stabilize the intermediate, and depending on the types of cation, the larger size, for example, cesium, is known for most active, and the for CC coupling, and also the pH of electrolyte also important. So having high pH condition is known for more efficient, and finally, the local CO2 concentration is also known to control the selectivity. So today, what I'm going to talk about why local CO2 concentration influences the selectivity on copper surfaces. And in order to do that, you need to understand, need to look at the reaction pathways of CO2 reduction and on copper surfaces. And this plot is not meant to be for your understanding. It just shows that it's very complicated and also still in debate. But in the simple version, looks like this. So in the copper, on the catalyst surface, CO2 is absorbed on the surface, and then the first electron transfer make the CO2 minus, which is the key intermediate. And also known for, and this step is known for the first reaction determining step. And then it's reduced to CO, and then the CC coupling also occurs to make the ethylene. Okay, so the important thing here to control the product selectivity between CO, carbon monoxide, and the ethylene is the CO binding energy, which is also called the key activity descriptor. So if CO binding energy with catalyst is too strong, then CO would not dissolve, then CC coupling occurs, right? So depending on CO binding strength, for example, if the binding energy is too weak, then for example, in the case for gold, silver, and zinc, then CO evolution is dominant. If binding energy is too strong, then CO2 reduction does not occur, and CO poisoning occurs, as you can see in platinum and nickel. And copper is the only has the optimum binding energy for CO-CO coupling or CC coupling to make ethylene and ethanol formation. But the real situation is a little bit complicated because with CO, you can the CO can be protonated to make the methane, and there is also the hydrogen and make the hydrogen gases. So you need to control all this the intermediate, and it's actually known that 16 possible reaction product including oxygenate and even the propanol, the C3 product on copper surfaces. The question is, how are you going to control those reaction paths? And the key is that in this reaction path is how much those intermediate are contribute on the surfaces. For example, if you have CO2, then you have CO and CO, neighboring CO and CO, then you get CC coupling. If you have CO and the hydrogen, then you form methane. And of course, you have the hydrogen, then you make the hydrogen molecule. And in a conventional process, that the applied potential controls this the contribution of intermediate on the surface indirectly. But what I want to do is we want to directly manipulate those surface coverages. So the one way to do is obviously you can control the CO2 partial pressure, the reactant concentration. Then you can directly control the CO2 concentration on the surface. Then subsequently, consequently, you can control the surface coverage of CO and CO and CO and other intermediate. Okay. So in order to do that, based on this idea that we use the gas-fed the flow cell for CO2 reduction. In the gas-fed flow cell, it's very similar to the fuel cell system. So conventional electrochemical cell that the Professor Yan showed in previous talk, you bubble the reactant in the electrolyte. But in this case, we flow the gas reactant at the backside of electrode, and our electrode is porous, so the gas will diffuse into the electrolyte interface, and the reaction occurs. And this is called gas diffusion electrode system, which used in the the commercial fuel cell system. When you do that, then you can have the very high current density, even exceeding ampere in the CO2 reduction. So we use the CO2 the reactant with various concentration by diluting nitrogen, and also we use a different the electrolyte pH using this system. Okay, so what we did first, we deposited copper by EV evaporation on the porous substrate, on the GDE. Since the substrate is porous, then the copper nanoparticles form on the surface uniformly over a very large area. And after test, we find very interesting behavior. So this showed that the partial pressure dependence of the Faraday efficiency. If you look at here, that so we only compare the Faraday efficiency of CO and the ethylene. So if you look at the CO, which is the square symbol, with increasing CO2 partial pressure, with increasing CO2 surface coverage, initially the CO evolution, the Faraday selectivity increases, and then it saturates, right? So initially it's about less than 5%, but after 100% CO2, you get 50%. But if you look at ethylene, CC coupling, become facilitated at low partial pressure, and the Faraday efficiency is about 50% for ethylene. But after 20% the CO2 partial pressure, the feed concentration, you can see that the Faraday efficiency actually decreases, even though you have more reactant on the surface. So you can say that the C2 is dominant at low CO2 partial pressure, and at high CO2 partial pressure range, C1 is dominant. So in order to look at why this, what this means, we plot a log and log scale to find the reaction orders for hydrogen and CO and ethylene. And if you look at the hydrogen, so hydrogen evolution occurs the surface recombination of adsorbed hydrogen molecules. But with increasing CO2 partial pressure, the reaction order actually decrease with order of -1. And then after 20% of CO2 feedstock concentration, it actually saturates. It means that at the CO2, 20% of CO2 feedstock, the surface is saturated with CO2, and we cannot find the neighboring hydrogen molecule to form hydrogen molecule. At this critical CO2 the concentration, you can see that the CO also somehow linearly increases, and after that, this critical concentration is sort of the reaction order decreases to about 0.3, and the ethylene even actually decreases. So ethylene, again, the CO and CO coupling should occur to form ethylene, but at high CO2 surface coverage, the ethylene, even though you have more ethylene, more CO coverage, it actually, ethylene formation actually decreases. So this means that the CC coupling occurs like a Langmuir-Hinshelwood mechanism on the surface recombination. So at low CO2 concentration, there's simply not much CO on the surface, so only hydrogen evolution occurs. In a moderate CO2 concentration, we have the the optimum surface coverage for CO coupling, but high CO2 concentration now surface covered by CO2, so it blocks the site to form CC coupling. So based on this the finding, we can know that the local CO2 concentration is key to control CO2 selectivity, and you must have a new strategy to find to control this local CO2 concentration. So in order to do that, we also need to look at the CO2 profile at the reaction interface. So from the gas phase to the GD, the gas phase to the electrolyte side, the gas phase, the CO2 concentration is constant, and then in the bulk side, CO2 concentration is 0. So you have a nice linear the CO2 gradient, and the local CO2 concentration is should be in the catalyst layer should be look this like the blue dot. So in order to control this local CO2 concentration in the catalyst layer, the obvious way is to decrease the CO2 partial pressure. Then you can decrease the CO2 the local CO2 concentration as appears in the red dot. And the other way is that you can increase the catalytic layer thickness. Then the profile is the same, but you push the increase the interface between catalytic layer and the electrolyte like this. Therefore, you can decrease the modulate local CO2 concentration in average in the catalytic layer. And third way is to control CO2 feed flow rate. So by changing CO2 flow rate, you can change the boundary layer thickness in the gas side, the gas chamber side. At that, cause the make the gradient different. So you can change the the average local CO2 concentration in the catalytic layer. And also, what he found is that when you use the CO2 during CO2 evolution, the solution becomes highly alkaline, and in alkaline solution, alkaline electrolyte, CO2 actually chemically dissolves into carbonate. So we are losing, the reactant in form of carbonate, and that makes effectively dilute CO2 the concentration or the CO2 partial pressure. So the feed flow also influence the local concentration. So we have 3 ways to control the local CO2 concentration. For example, you can change the flow rate. You can change partial pressure. You can also change the thickness of catalyst layer or the porosity. So we also did, to verify our idea with this 1D simulation provided by Dr. Joel Ager at LBNL. When you do the calculate the local CO2 concentration as a function of the CO2 partial pressure, you can see that obviously you can change the concentration, and you can also do some the modeling with different thicknesses, and of course you can change the modulate local CO2 concentration as expected. Okay, so in order to verify again our idea, we make a model particle catalyst system. We use copper cuprous oxide nanoparticle with about 60 nanometer in size. And in order to control the particle thickness, the catalyst layer thickness, we use 3 different deposition method with the same catalyst loading. We use, for example, drop casting. We also use a hand painting, and then we also use the airbrushing method to control the evaporation rate of the ink. And if the evaporation rate of ink is slow, then you get very dense, catalyst layer, as you can see in this SEM image. But the airbrushing, the method, deposition method, produce highly porous catalyst layer, even though all 3 has the same catalyst loading of 0.6 milligram per square centimeter. Now the Faraday efficiency shows quite dramatic impact of this. Even though we are using same catalyst materials and same catalyst loading, you find that the ethylene production is about 2 or 3 times increased when you use thick porous copper oxide. Okay, so initially it's like less than 10%, but under the right condition, if in the airbrush sample, it's above 50%. So I think that it verify our idea. The second is the modulating CO2 partial pressure, and as expected that 75% CO2 in our cases is produced more 10% more C2 product than 100% CO2. And we also tested the flow rate, and we see that decreasing flow rate actually increases the CO2 partial C2 product. So CC coupling is also enhanced with a lower CO2 feed flow rate. So we can construct the CO2 the contour plot to optimize the C2 product Faraday efficiency as a function of CO2 concentration and the flow rate. Our default condition for drop cast, it's about 25% Faraday efficiency for C2 product, C2 plus product, but when you use the optimizing the feed flow conditions and the deposition method, you can get about 61% C2 product Faraday efficiency. Now you can further optimize the particle size and thicknesses, loading amount, and so on and so on. You can achieve the Faraday efficiency more than 70% at even at 500 million per square centimeter, which is, as you remember the techno economy evaluation, this make the whole this process profitable and also have the environmental impact. And this shows that our data is one of the best performance, is one of the best performance reported in 2020. Last year, right now, somebody beat this, the performance metric, but we show that still our data is one of the best, and it's also stable over 10 hours. Okay, so this is just summary that I'd like to point out that electrochemical CO2 reduction is promising CCU technology, and to produce the ethylene, you need to have the control the local CO2 concentration to have the ideal surface coverage for CCA coupling. And finally, I'd like to thank my student and the funding resources, especially Hakhyun here and Bobby are two main drivers for this work. And the Bobby here, he's actually who was postdoc in our group. He actually ultimator of NUS, unfortunately. Now he returned to Singapore, and he's the researchers in A-STAR. And I'd like to finally, I'd like to thank my funding sources like Carbon2X project, which is a large project that we are looking at how to, in collaboration with industry, how to commercialize, this process. Thank you for your attention, and I'm happy to take questions.
Okay, thank you very much. Let's have questions for Professor. Any question from the audience? Shujo. Yep. Yeah, you can go ahead and then ask your question.
Okay, very nice talk. So for me, it's a little bit of surprise when the lower particle pressure get a more C2 plus product. So I was wondering if you can measure the mobility of absorption reaction intermediate, because at the low reaction, it's hard to think about the 2CO absorption. It's nearby to have the coupling reaction. So maybe the mobility of CO at the low concentration is high. So they need some time to diffuse to the nearby region.
Yeah, thanks for, I think that's a great question. So you have to consider mobility, yes. But in reality, I'm not sure how can measure the mobility unless adsorption mobility in electrochemical environment. I'm really happy to get some ideas from your side. So I have no idea how to do that. But yes, it's possible, but especially bottom the high concentration range when the site is blocked. I mean the HER actually tells how the situation out there. So at the 20%, the partial pressure, the HER actually suppressed, means that all the surface is covered with carbon containing species.
Yeah. Okay. But maybe we can talk about this offline.
Yeah.
Okay. Thank you.
Okay, so and we have another question from Daniel. Daniel, yeah, you can unmute yourself.
Thank you for the talk. Thanks for wonderful talk. I actually I found out about this work and also about your postdoc Bobby, and I actually, because I know him in Greece, so I actually
Okay.
invited him
Yeah.
here today. Yeah. So my question is, first thing, because some of the papers they don't just do copper, but they do alloys like copper silver or copper
Right, right.
aluminum.
Mhm.
So, how applicable is the trend for CO2 concentration and partial pressure the same for these materials? And the other question I want to ask is also, um, is this also shown to could it be shown to be the case also for, say, instance, ethanol on catalysts that are more selective for ethanol, maybe some of those copper oxide, maybe they are found to be ethanol. So since that is C2, that also should be the case, right?
Yeah, it's a very great questions and also difficult task. So the alloy system is a little bit complicated, especially copper and silver is very complicated because they don't mix well. So it forms the phase separated, catalyst, like so copper on, well, so silver on copper, like something like that. And since those alloys, the silver, for example, is known catalyst for CO, carbon monoxide, right? So the silver also activate CO2 into carbon monoxide, and carbon monoxide itself can be reduced to ethylene and other products on copper surfaces. So it's called a cascade reaction or the tandem reaction. So it's complicated, but I'm not sure I personally, so my group tested copper silver system, but we tested like copper nickel and copper zinc, and all those cases the partial pressure dependence actually just similar. So at low partial pressure, actually ethylene formation is enhanced at given over potential. And what was the second question? The selectivity between ethylene and ethanol, right?
Yeah, ethanol.
Yeah, so selectivity between ethylene and ethanol is much difficult than CO and C2 product, because ethylene and ethanol, they shares a lot of intermediate after CO. So it's difficult, but one suggestion is to use alloy system, and to make ethanol instead of carbon, the oxygen must connect, bind onto the catalytic surface. So you have to have some type of alloy system to make the oxygen bond on the catalyst. And my understanding is that copper zinc alloy system is known to enhance the methanol production and suppress ethylene formation.